Okay, yeah, good morning. So let's get real. So this picture here is a picture of a four-dimensional convex polytope. It's a direct product of two triangles. So just while people come in, so that's a four-dimensional polytope. It has 9 vertices, 18 edges, 15 two-dimensional faces, and 6 facets. The facets are three-dimensional polytopes. They're all triangular prisms, or Toblerone in Swiss German. And we're gluing together these 6 Toblerones to make a three-dimensional sphere. Notice that the vertices are labeled by the pairs of a 5-element set, except for 1, 2. Right? So there are 10 pairs in the set 1, 2, 3, 5, and there's a labeling. And we're going to get to this polytope maybe later towards the end of the talk. But again, it's always good to have something to think about during a talk. So this is the direct product of two triangles. And maybe you can try to think a little bit about how to visualize this and what the combinatorics of such a four-dimensional polytope is. So this talk will be based on a paper called Kinematic Stratifications. And the two co-authors, so Veronica Calvo, she's a PhD student in Leipzig, and Hadley Frost, who is sort of a physicist, I would say. He is a postdoc at the Institute for Advanced Study in Princeton. And today we're going to get real. So this in particular means we're going to address the question that Claire asked yesterday, namely, what are the semi-algebraic subsets? What are the semi-algebraic constraints, the inequalities that hold for our kinematic spaces if we focus on the real numbers? Here's the setting. As before, particles are represented by momentum vectors. Here I'm looking at 1 plus d-dimensional Minkowski space. So momentum vector here in this notation has d plus 1 coordinates, p0, p1, up to pd, with the familiar Lorentzian inner product. And p dot p is the quadratic inequality that defines the ice cream cone. And the speed limit says that we're supposed to stay inside. Every particle is supposed to stay inside this closed cone, but they are allowed to be on the boundary, in which case they're massless. So, of course, these things have names. So, for example, massless particles are photons, or massive or proton. And the context is, again, positive geometry and particle physics and cosmology. Okay, so here is Veronica, the co-author, and she's holding the light cone, right? Now notice that the light cone has two components, right? There's the future and there's the past, right? And then, you know, people come in, particles come in from the past, something happens, and then they go off into the future, right? So this is sort of where the scattering process takes place. It's interesting. So the relationship here and the sort of being in this light cone and whether, for example, the difference of two vectors is in the cone or not. So if two particles are such that their difference is not in the cone, then they're causally independent, right? So if I'm a particle and Nicholas is a particle, but you know, if our difference vector is not in this cone, then neither of us can influence the other, assuming we obey the speed limit, right? So that's independence. Of course, dependence means that our difference vector is in the light cone, and this leads to a notion of causality. It's kind of interesting. So in statistics and data science and computer science, there's a notion of causality and causal inference, and causal inference, of course, has been looked at also algebraic geometrically. But I think there's a disagreement between physicists and statisticians what causality is. And I actually saw almost a fist fight among Max Planck directors in the so-called Perspectives Commission once. So I think there's an interesting debate what causality actually means. In any case, so here's Veronica, and d is equal to 2 in the picture, and we're going to be interested in points that are inside this cone, and we like to talk about configuration spaces, real semi-algebraic sets of configuration of n particles in the light cone. I'm going to write p upper 1 up to p upper n for these particles in our d plus 1-dimensional space. The Lorentz group SO1d acts on them, and of course we like to record invariant properties. Okay, so we're going to be interested in this closed semi-algebraic set Veronica is holding in her hands. That's what we're going to be interested in. Okay, let's recall, so the Mandelstam invariants are the entries of the Gram matrix. So here I have this matrix where the momenta are the row vectors, so that's an n by d plus 1 matrix. Then I have my quadratic form, that's a symmetric d plus 1 times d plus 1 matrix, and here I have the transpose, that's a d plus 1 by n matrix, so that's a low rank symmetric n by n matrix. And notice here I do write the SII on the diagonal, so from the outset I will later assume that it's massless, but for now let me keep the SII on the diagonal. So the semi-algebraic set, Nicholas, that we're going to be interested in, I'm going to call this the Mandelstam region, MNR. So this is the semi-algebraic set of these matrices, so all matrices that have such a representation for a fixed rank R. So I'm fixing N, I'm fixing R, and then I'm going to assume I have such a factorization over the real numbers. Now, this is going to be a semi-algebraic set, and the codimension of the semi-algebraic set is the same as the codimension of its Zariski closure of the variety. And this codimension is n minus r minus 1 choose 2. And this takes place in the ambient space of symmetric matrices, which has dimension n plus 1 choose 2. So what we're going to be interested in, we're going to carve up this region, this semi-algebraic set, into pieces according to the signs of Sij. I'm going to stratify this according to the signs of the entries Sij, and so each entry here could be positive, negative, or 0. And this will give us a stratification or subdivision, right? It may or may not have good properties, so this will give us a partition of this set. Here I just mean a union into other semi-algebraic sets. Right? So just let's take this naive, not going to make any fancy topological assumptions as the ones that Melissa mentioned here just on the outset. I'm going to get to topology later. Here I just mean it's a union, stratified into pieces. Yes. Well, I don't have to, but I think it's quite natural to think about where does this come from. You know, I'm fixing space-time dimension. I like to kind of think about the number of particles as some fixed number n, and space-time dimension is some fixed number d or d plus 1. This seems like a natural, fairly natural assumption for us. Just like you look at the Grassmannian GKN, and n and k are fixed, but of course you could also fix n and vary k, or you could go to classifying spaces and send n to infinity. So I'm also fixing a d for the rank, and n for the number of particles. Oh, I see. Why do I fix? That's a good question. So R could be d plus 1. Let's see how this goes. Yeah, so I'm going to introduce an R and a D. This makes it a little nicer to sort of talk about the pieces in this stratification. Okay, so let's talk about being Lorentzian. So what's happening on this slide is that in mathematics, and in particular in combinatorics, everybody loves Lorentzian polynomials. So there's something called Lorentzian polynomials and Lorentzian combinatorics, and people are very enthusiastic about this, especially since Juni Ha won the Fields Medal for work in this topic. But of course, Lorentzian comes, from our Minkowski space in physics. So on this slide, I'm going to put together Lorentzian polynomials from math with the Lorentzian inner product here in this setting. Let's start out. So the Mandelstam region consists of matrices S. Well, this is sort of a description of what they are. So the diagonal entries are non-negative, and S has one positive eigenvalue and R minus one negative eigenvalues. And here we're seeing why I'm stratifying by rank. So if the rank is exactly R, and there are non-zero eigenvalues, and Lorentzian says that one of them is positive and R minus one are negative. And this comes from this diagonal factor in the middle. Right? So if you give me a matrix, if Claudia gives me a matrix, I want to check, is it in the Mandelstam region? One way to test this is to look at the eigenvalues. I'm going to say the Lorentzian region is the subset here where this is an entry-wise non-negative matrix. So if this matrix happens to have, if all the Sij's, including the diagonal, are non-negative real numbers, I'm going to say the matrix is Lorentzian, and I'm going to call this the Lorentzian region, denoted LNR. Okay, I'm going to write, if I write less or equal something, then I mean, I'm allowing everything, right? So less or equal R means it could be R or R minus 1 and so on. Well, the remark I just made, to be precise, so Ln less or equal n, meaning the union of these over R, those are precisely Lorentzian polynomials of degree 2. Okay, so I'm identifying quadratic forms and square matrices. Square matrix is Lorentzian if it corresponds to a Lorentzian polynomial. And if you know what a Lorentzian polynomial is, then this is a remark. And if you don't know, then it's a definition. Now, so this was studied by Juni He and collaborators, for example, Peter Brandane. And Brandane has a nice statement about this space. So he proved that this is a topological ball of the full dimension, n plus 1 choose 2. So this is a little bit the analog to the positive Grassmannian. And furthermore, if we stratify, according to rank, then it's a disjoint union of different balls, namely 2 to the n minus 1 such balls. Now, in the meantime, there is a more recent paper by Matt Baker, Juni, Mario Kummer, and Oliver Lorscheid called Lorentzian Polynomials and Matroids over Triangular Hyperfields. And the stratification that I am discussing is compatible, matches theirs in the special case where rank is 2. So if I'm restricting to non-negative matrices, I'm restricting to my L region, and the stratification I'm about to describe matches those in this paper. Okay, so the short version of this slide is, so the excitement about Lorentzian polynomials and combinatorics matches, these spaces that are quite natural from a kinematic point of view. Okay, let me give you a different characterization of membership so that you can use, which is more of a semi-algebraic description where you don't have to compute eigenvalues, right? So computing eigenvalues is a painful thing, right? You have to go to a field extension. You have to write down, square roots and even worse things. So here we can do this over the ground field. So a matrix S is in the Mandelstam region if and only if it has rank R and the principal minors have alternating sign. So by Si, I mean the square submatrix with set of row indices I and set of column indices I. And then I'd like the determinant to have a specified sign. So the 1 by 1 minors are positive, the 2 by 2 principal minors are negative, and so on. And so this is the condition, and that's an if and only if. That's equivalent to this description. Now, of course, that's reminiscent for those who come from statistics or optimization. I said yesterday that positive definite matrices are ones that we like. And of course, this is the sort of the signed Lorentzian version of the familiar characterization of non-negative, negative, positive definite matrices by positivity of the principal minors. Now let's work out what these minors are. So if I has cardinality 2, so if I is the set ij, so then we're saying that the ij minor is non-positive, so that's this inequality, and then the 3 by 3 minor with row and columns ijk is non-negative, that's this inequality. Okay? So those are the inequalities that describe our region. Now it's a little exercise that this inequality together with this inequality implies the following, namely the product Sij times Sik times Sjk is non-negative for any 3 indices. So if you play with these two things, you get this inequality. Now you have 3 numbers whose product is not allowed to be negative. So this has some strong consequences, and it can be summarized in the following proposition. So if S, for example, let's concentrate for a moment, let's say these are all non-zero, right? So I have 3 non-zero numbers whose product is positive. Okay? Well, either all 3 are positive, or 2 are negative and 1 is positive. And that implies the following. So if S is a matrix in the open part where all the entries are non-zero, then there exists a sign vector of length n such that Sij in sign is equal to sigma I times sigma j. Try this. Suppose you have, a 4 by 4, let's say we're in the 4 by 4 case. Right? And for any 3, I have this condition. Right? Now, of course, let's also say they're distinct, right? So let's say there's the 4 of us, right? Any pair has a sign, right? That means we like each other or we don't like each other. Okay, so the 6 of us, there's 6 signs, between us, okay? But the condition is that we have to like each other enough, right? So the product along triangles has to be positive. This means that each of us has a sign, likable or not, such that the product, that Sij is the product of the likability of I times the likability of j. Is clear? I'm saying something completely elementary. Okay, but that's a very, very important. This really restricts the combinatorial sign patterns, right? Because it looks like from the offset there's a quadratically many sign patterns, but actually there's only linearly many, right? So rather than having to specify quadratically many signs, right? So now there's n people who pairwise like each other or don't, right? I'm saying it only depends on the likability. Every person has a plus or minus, whether they are likable or not, right? And then 2 people who are both likable, well, they like each other, and 2 people who don't like each other, they also like each other, and that's how it goes, okay? Very good. Oh yeah, so this is my yes. I don't think for PSD matrices, it's really the inequalities have to go this way to get this, right? So this one we have for PSD, this one we don't have for PSD. This is really a Lorentzian property. All right, yeah, so I said, causality, so here's the light cone. This is the light cone again, and now D is 1, right? So this is the D plus 1-dimensional light cone. Now, if these particles have mass, then these are the mass shells, right? So we heard a lot about on shell and putting things on shell. So shell is simply, so the light cone is the quadratic form equals 0, right? And a shell is the quadratic form equals some other number, like m squared. And so the ith particle might be on its shell, so the first particle is on its shell m1, right? So this says that p1 dotted itself is on this irreducible hyperboloid, and so on. But if the third particle is massless, then it lies on the blue boundary. Okay, so a corollary to the previous little combinatorics lemma about liking and not liking each other is the following. So the Mandelstam region is the union of 2 to the n minus 1 signed Mandelstam regions. And so by m n sigma r, I mean, I'm specifying weakly, let's say, or strong, I'm specifying the sign of each entry, and I only have 2 to the n minus 1 top dimensional regions. So the relative interiors are pairwise disjoint, and these sign vectors distinguish the future from the past. Right? So rather than having n people who like each other or not, have n particles, right? And some of them are in the future, and some of them are in the past. And then the inner product, the sign of the Mandelstam invariant, simply tells us whether they are in the same piece of the cone or whether they're in opposite pieces. So put all the likable particles in the future, right? All the non-likable particles in the past. We want to forget about them, right? And this is the stratification. Linearly many. Now, Lorentzian region is the closure of this all plus region. So if sigma is plus, 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 then it's the Lorentzian region. That means everybody is either in the future or everybody is in the past. That's the Lorentzian quadratic forms. Okay, we have a lot of time, so please interrupt me with questions. This is the first course subdivision, so I'm saying, there are not so many pieces. And they're indexed by sign vectors. All I need to tell you who is in the future and who is in the past. Okay, so from now on, we're going to do 2 assumptions. So the first assumption is we're going to assume that the particles are massless, but I am not yet requiring that momentum conservation holds. So in about 15-20 minutes, momentum conservation will hold, but I'm now putting the first assumption in, namely the particles are massless, but I'm allowing, just for now, momentum conservation to be violated. Okay, so if the particles are massless, then the diagonal entries are 0, and I'm using this notation, M0nr. So this is all the Mandelstam matrices, n by n, of rank exactly r, that have zeros on the diagonal. All right, now we looked at the 2 by 2 minors and the 3 by 3 minors, so let's look at the 4 by 4 minor. So the determinant of such a matrix, if I take the 4 by 4 principal minor with rows I, j, k, l and columns I, j, k, l, then this determinant looks like this. This one, and it's supposed to be non-positive. Remember, even size is supposed to be non-positive. So now I'm going to do something amazing. So this is a semi-algebraic set. I'm going to rewrite this in a somewhat surprising way. Okay, so buckle yourself. What I'm going to do is I'm going to formally replace Pij by the square root of Sij. Okay, might as well, right? So, of course, this has degree 4 in the S's, so after the substitution, this will have degree 8 in the P's. Now, it turns out that this polynomial of degree 8, homogeneous polynomial of degree 8 in the P's, factors into 4 quadratic factors, and it factors exactly like this. We say this again. So I take the 4 by 4 minors, that now the diagonal is 0, and I make this harmless looking substitution, and now afterwards it factors into these 4 pieces, and these 4 pieces are up to sign the Plücker relation. So what math people call the Plücker relation, and what the physicists call the Schouten relation. Okay? And this is related to this process. I earlier talked about the squared Grassmannian, and I pointed out the remarkable fact that the square of a real number is always non-negative. And it's this transformation that also, this is important in statistics. So Hannah Friedman has a paper called The Likelihood Geometry of the Squared Grassmannian. Now, what's important about this transformation? This guides us to the Plücker relation, and this guides us to matroids in a setting where we didn't expect them. So I didn't put matroids in. There was no Grassmannian, there was no matroids, right? There was just these, there's just this Mandelstam region. But now suddenly, I'm seeing here Plücker relations appearing, and this guides us to matroids, and that's why we're going to look at matroids in the next slide. This is for any IJKL. Yes. This is for any, so distinct. So IJKL are distinct elements in the set 1 up to n. I look at any 4 particles, and they satisfy this thing. Yeah. This is an unexpected appearance of the Plücker relation. It's not the Plücker relation, it's the same Plücker relation, but it appears for an unexpected reason. And it's the same reason. So if you read this really nice paper on, okay, whether or not you like triangular hyperfields, that's a bit of an acquired taste, right? But whether or not study the topology and the topological structure of Lorentzian polynomials, there are matroids, and there are Dressians, and there are tropical Grassmannians where they shouldn't be. Right? And this is the reason. The reason is this thing. Yes? Yes, completely irreducible. Very nice K3 surface. Okay, so let me talk about matroids. So in this lecture, every matroid has rank 2. Okay, just today, in this lecture. Now, there are 2 possibilities for people in this room. Either you know about matroids, then what I'm about to say is a remark. Or you don't know about matroids, then take this as a definition. I'm going to give you a definition of matroid that's very elementary, but it only applies to rank 2. So for the purpose of this talk, a matroid, that is to say a rank 2 matroid, is a partition, a set partition, P1 up to Pm. So these are parts these are non-empty sets in 1 up to n. So I'm partitioning the set 1 up to n into m pieces. Okay, I'm going to say the bases of this matroid P are pairs U and V, where U and V are in a different part. So like maybe n is 20, right? So I'm making a partition here, and if I take 2 people who are in a different set, I'm going to call them a basis. Okay. Now actually, I wrote here of a subset, and I meant it. So there are some people who don't participate. Right? So again, let's do this. So we have n people in the room. Some of them I'm sending out. You're not participating. And the rest of you gets partitioned. And then bases are pairs coming from distinct parts. Now, if you were sent out, I call you a loop. Okay? So the people who don't participate, they are the loops. Okay, so in the matroid I'm assuming that this is non-trivial, so m is at least 2, and then the number of loops is n minus the cardinality of p, by which I mean the cardinality of the union of this disjoint union. Okay? So for example, one way to partition this is nobody is a loop, everybody stays, and everybody is their own part. This I'm going to call the uniform matroid. Okay, now I'm going to define a signed matroid. Okay? So if you know what an oriented matroid is, forget it. This has nothing to do with oriented matroids. Okay? So by a signed matroid, I mean simply a pair of a matroid in this sense and a sign vector. But this is a sign vector on those people who are not loops. So everybody who is not a loop now gets a plus or minus. Okay, and then I'm going to define the stratum M0 P sigma R is the subset of the massless Mandelstam region. So the massless Mandelstam region was the Mandelstam region with zeros on the diagonal. And to be in this stratum, well, the sign of Sij is sigma I times sigma j, right? So I take the non-loop people, and they're likable or not, right? And that defines the sign of Sij if they are not in the same group. But if they're in the same group, then Sij is 0. So if I have a basis, and I'm giving this basis a sign, Sij, and then Sij is 0 if I and j are in the same part of the partition. And this is equivalent, to matroids of rank 2. So for the purpose of this talk, this is the definition of matroid, and signed matroid, I simply mean this, and I'm giving a sign now to each entry. Okay, now we're reaching the half point. So here's a first theorem. I'm going to fix the rank R to be a positive integer. Then I'm going to say the massless Mandelstam region, Mn upper 0, is the union of strata that I just described, M0P sigma R, and it's the union over all signed matroids. So the signed matroids, as defined on the previous slide, they index the pieces in this massless Mandelstam region, and the pieces are given by the signs of the entries, but the allowed signs of the entries come from the combinatorial description that I had on the previous slide. And remember, the description is, I'm going to send some of you out of the room, we partition the rest, right, into M pieces, and then, I'm giving a sign to each basis, and basis means a pair coming from different parts. Now, I'm going to call this thing a kinematic stratum. So kinematic stratum is indexed by R and a signed matroid sigma. Well, I said that this is the disjoint union, but I didn't tell you yet whether this is non-empty. Right? It could be that this blue M set is empty. So down here is a condition about when it's non-empty. So it's non-empty if and only if either R is at least 3 and at most M. Remember, M is the number of blocks in the matroid. M is the size of the underlying simple matroid. Okay? M is the, okay? So if the rank is between 3 and M, then we're okay. Or R and M are both 2. There's a simple combinatorial condition on the rank and on the number of blocks, and that's if and only if this semi-algebraic set, which I call a kinematic stratum, is actually non-empty. Now, if it's non-empty, we can ask what is the dimension. Not only varieties walk into the door and we ask for their dimension, sometimes semi-algebraic sets walk into the door and we ask for their dimension. So the kinematic stratum, the dimension is M times R minus 2 plus N minus I minus R choose 2. So what are these things? So I is the number of loops. So I is N minus I is the number of people I send out of the room. Okay. M is the number of blocks, R is the rank, and N is the number of particles. So this is a non-negative integer, and this is the dimension of the kinematic stratum. So the kinematic stratum is given by one of these Mandelstam matrices, zeros on the diagonal, and a sign specified. But to specify the sign, I have this language of rank 2 matroids. And again, Claudia, the matroids appeared for reasons other than those that you think of. Okay, that's our first theorem. I know what Lorenzo is thinking. Lorenzo is thinking, why don't you do massless? Well, we're going to do massless in 10 minutes. I'm just kidding. I'm kidding. No, we're going to do, I'm sorry, momentum conservation. Why don't, sorry. You really, in physics, we need momentum conservation. So this is without momentum conservation. There will be a version in 15, 20 minutes, with momentum conservation, but it's more complicated, right? So there's matroids and there are these things, but these things will get a little bit more complicated when we have momentum conservation. And we'll see that in 20 minutes, 15. Well, that's going to be a sub. We're going to get to momentum conservation. Let's maybe talk a little bit more about these pieces and the topology of these pieces. So after all, we should look at topology and balls and how they fit together. So let's talk a little bit about this. Okay? Okay, but before we get to tautology, let's do a little bit of combinatorics. Okay, a little bit of the numeric. So here I said, what are these strata, right? I have these kinematic strata, and I told you which ones are non-empty and what the dimension is. So now I like to tell you how many there are. I like to tell you how many strata there are, okay? Okay, so I'm going to use this notation, curly parentheses, n minus I over m. So this refers, called the Stirling numbers of the second kind. So this is the number of set partitions of a set with n minus I elements into exactly m parts. So that's a combinatorial number. Okay? So then the number of kinematic strata of a given dimension d is given by some combinatorial formula. Well, I'm sort of turning this back now. Here I said, here's a stratum, and if it's dimension, I'm sort of turning this on its back. I'm saying, let's fix this number to be d. How many strata are there? Okay, well, and if I'm fixing the sign sigma, so if I'm fixing who is likable and who isn't, if I'm fixing who is in the future and who is in the past, then the number of strata is I'm summing over all m greater or equal r and choose L times this Stirling number. But if I'm altogether running over all sign patterns, then I get this version, right, with a power of 2 multiplied. And here I'm allowing sign patterns sigma. Of course, they have zeros or pluses or minuses, right? Because that's built into my matroid story. So my matroid story says a pair of people in the same group, their sign is 0. This tells us how many strata there are. Okay, so it's fun to make tables, right? For example, with 4 particles. So here is the space-time dimension, 1, 2, up to 6. Maybe here is the rank I'm specifying. And then this is the dimension of the stratum. This is the rank. So if I look at 4 particles and maybe at rank 3, right? So there are 4 non-negative strata of dimension 4, 6 of 3, 6 of dimension 4, and 1 top one. And then I'm going over all sign patterns. I get these green numbers. And then here's n equals 5. So this is simply the F vector, the face vector of cells, pieces in the stratification. And I have not yet said whether or not these are nice cells. I'm just counting, how many kinematic strata there are. And I can either count for a fixed sign pattern or I can count over all sign patterns. The I is part of the matroid. Right? So I'm fixing sigma. Remember, I'm fixing here. So this is the number of kinematic. I'm sorry. What am I doing? Oh, no. I is determined by sigma. So I'm counting all the strata over all sigma, and then I is part of sigma. Right? So sigma is the sign matroid. I'm fixing sign matroid. I'm saying how many people leave the room, and then we have these signs. Okay, that's counting. Now let me tell you about the poset. So the poset says when is the closure of one stratum, when does the closure of one stratum contain another stratum? So now I'm defining a poset, a partial order, on the set of matroids, as defined here, and on the set of signed matroids, as defined here. So let me do this in the all positive case. So I'm going to focus on the Lorentzian region. So L0NR is the Lorentzian part. Okay, I'm going to say a matroid P is less or equal to another matroid P prime if every loop of P prime is also a loop in P. So if in the P prime story, whoever gets sent out also gets sent out in P. And the partition P prime refines the partition P. This defines a partial order on the set of rank 2 matroids. Now, there are many, many different definitions of matroids. One of them is by matroid polytopes, and this is equivalent to containment of matroid polytopes. Right? So if you know about the second hypersimplex and the matroid polytopes it contains, then this is inclusion of matroid polytopes. Okay, let's do an example. So for example, if n is equal to 4, r is equal to 3, there are 11 strata. That's 1 plus 6 plus 4. And I'm just focusing on the Lorentzian region. So I'm focusing on Lorentzian quadratic forms. So I'm fixing the uniform matroid. Nobody gets sent out and everybody is in their own partition. So this means all the signs are plus or minus, right? So this has 3 connected components. The top stratum has 3 connected components. So in particular, the cells are not connected. Right? So unlike positive regions, positroid regions, these cells, I didn't say they're connected. They're not connected. This one has 3 connected components. And the way to think about this is as follows. It's the union of 3 curvy squares. And the way they're glued is as follows. Take a tetrahedron. Now, a tetrahedron at its boundary contains 3 4 cycles. Okay, so this is the complete graph, the boundary, the edges of a tetrahedron is a complete graph on 4 vertices. And in a complete graph on 4 vertices, there are 3 4 cycles. Like we go this, or we go that, or we go this way. Right? So there are 3 4 cycles. Mark this 4 cycle in the bound, make this frame, build this thing, out of wire, right? And I may put some glue on the 4 cycle and dunk it into soap and pretend the soap sticks at the glue. That makes a curvy square. And you do this for each of the 3 4 cycles, that's the stratum. It's clear? So you take a tetrahedron. There are 3 4 cycles. You glue in a quadratic surface. In fact, exactly your quadratic surface from yesterday. You glue this in 3 times, and that gives you the top stratum. Now, we can extend this definition of poset of matroids to signed matroids. So I'm going to say a signed matroid P sigma is less or equal to another signed matroid P prime sigma prime if P is less than P prime as a matroid, and on the non-loops the signs agree. Very natural way of extending. So with this language, so now I've told you how many strata there are, I told you how many there are of a given dimension, and I've given you an indexing scheme. I've given you, a poset that indexes these strata, and already hinted at the fact that these strata may be disconnected.
The 3.
Yeah, this is a bit of a bad picture. You should think about this as 4 curvy squares. The best way is to see this inside a tetrahedron. I'm claiming inside a tetrahedron, there are naturally 3 curvy squares. And the reason there are 3 rather than just 1, right? On the positive cross-member, the positroid, yesterday, there was 1. But then, Claudia said, what about all these weird other signs? Well, they are accounting for the other squares. Yes? And we don't even have mass conservation yet. It's all about physics. All I'm talking about the kinematic region. I'm talking about the semi-algebra. I'm taking over the real numbers. I'm telling you what are Mandelstam matrices. I'm organizing them according to rank and sign pattern. Precisely, not more and not less. I'm providing a language to talk about Mandelstam matrices. Matrices Sij. Okay, topology. Yeah, so our stratifications are actually nice. So if a stratum intersects a closure of another stratum, then containment holds. So if I have 2 stratum, and if one intersects the closure of another, then they're actually contained. However, the individual strata have interesting topology. So M0, lower P sigma 3, okay? That's rank 3. has m minus 1 factorial over 2 connected components. So that number is 3 if m is 4. So m people, go to a Chinese restaurant, they sit around a big table. There are this many ways of arranging themselves. Doesn't have to be Chinese, any restaurant. Right? So you go to a restaurant, how many? This is the number of cyclic permutations of an m element set. Now that is, of course, familiar to those who, in physics, right, you study Park-Taylor formulas all the time, right? And indeed, this is related to the moduli space. So here's a little theorem. So the kinematic stratum, this Mandelstam stratum, and I'm going to take rank less or equal to R to make it closed. So this has the homotopy type of a topological space called the configuration space. And this is the space of m labeled points on the R minus 2-dimensional sphere modulo the symmetry. So this is the configuration space, but modulo rotations of the sphere. So for example, if R is 3, then these are m labeled points on the 1 sphere. And the 1 sphere is the boundary of a table in the restaurant, whether it's Chinese or Austrian, right? We sit around the table, and the boundary is a 1-dimensional sphere, and that's, the topology. But in general, it's the homotopy type of a configuration space. Of course, these configuration spaces have been studied. So, for example, in topological combinatorics, there's a very nice paper by Feichtner and Ziegler from 2000, so the integral cohomology of exactly these things. Now, one case that's quite nice and relevant for physics is the case where R is equal to 4, right? So if R is equal to 4, I'm talking about configurations, labeled configurations of m points on the sphere. We can think about the sphere as the Riemann sphere, might as well, right? Then the stratum is homotopic to the moduli space, M0, MC. So this is configurations of m labeled distinct points on the Riemann sphere. The favorite moduli space of every algebraic geometer, and hence to the complement of the affine braid arrangement. So this slide says, what this slide says is the strata themselves have interesting topology. Unlike in the positroid situation where the strata are balls, here the strata have interesting topology. Maybe you're a little lost in the details, but all I'm doing is I'm describing the combinatorics and topology of organizing Mandelstam matrices, that is to say, kinematic data over the real numbers. Very good. So here's Stanley Mandelstam. I promise we're going to talk about him. So Mandelstam in 1958 wrote this paper, Determination of the Pionuclein Scattering Amplitude from Dispersion Relations and Unitarity. And in this paper, he has this picture. That's figure 1 in this paper. And he talks about reactions 1, 2, and 3, and the kinematic. So this is some kinematic space in this 1958 paper. Now in math, especially in fields such as algebraic geometry, the strength of the field comes from its history. Right? This algebraic geometry has gone on for 200, 300 years, and it's exactly this history that is sort of responsible. There's these historic questions. The very, very long historic development leads to this very powerful edifice that we have today. So I always tell my students, whether they like it or not, usually they don't like it, I always tell myself, please read a paper from the 19th century. Right? Because that's where it begins. If you want to understand 21st century abstract, say, algebraic geometry, it's extremely helpful to go back 150 years and look what people did in 1870, maybe. Right? But then students often say, I don't know, this is like written in like weird languages like German, True, that's true. Some of these papers are written in unfamiliar languages, especially now sometimes Italian even or French, right? But it's not so bad. Some of them are translated, and in fact, they are excellent authors. Sylvester Cayley, I recommend, if you have nothing else to do tonight, read the paper by Arthur Cayley. They're fantastic, and in English. Okay, very good. Now, the analog in physics would be maybe not quite 200 years ago, but maybe 70, 100 years ago, maybe you want to read an article by Schrödinger, right? After all, you are in the Schrödinger Institute. Or maybe a little later, you could read an article by Mandelstam. Okay, so I'm going to develop this now, and I'll tell you what Mandelstam picture is. But to do that, I need to now finally do what I have to promise. I have to throw in momentum conservation. I'm going to say the massless momentum conserving region, I'm going to call that C, upper 0, lower nr. So C for conservation, right? Is the following. It's the same thing. It's the same union as before. I'm going over all signed matroids, C, 0, P, sigma, R. But now I'm intersecting the previous region. The previous region, we just discussed how many there are, what the dimension is, what the topology is, how they fit together. But now I'm taking the previous region and I'm making the row sums all 0. I'm now taking my symmetric matrices, and this is codimension n linear space that for each for each particle I from 1 up to n, the row sum is 0. I'm sorry, for each, so I'm summing, I have an n by n matrix, symmetric, the rows and columns sum to 0. Okay, so that's and then what's left is a linear space of dimension n times n minus 3 over 2. All right, now there's also a theorem. So the same theorem, so I had this theorem. So I had the theorems that say how many there are, what are their dimensions, and so on. So this also holds in the massless case. So the massless momentum conserving region is non-empty. This blue thing is non-empty if and only if some combinatorial condition holds, except now the combinatorial condition is a bit more complicated, right? So either R is between 3 and m, right? And then there exists I, J, K, L among the n particles, where I and J have the same sign, likable or not. So they're both likable, the other ones are dislikable, such that the restriction of the matroid P to this 4-element subset is either the uniform matroid or is this two pairs, two parallel pairs. So maybe the difference, never mind the difference. This is some technical combinatorial condition. But this technical combinatorial condition says this is exactly the condition when this is non-empty. Or there's the other case where R is equal to m and each part has elements of opposite sign. So this 1 and 2 gives a complicated but precise combinatorial condition when there's a Mandelstam region with mass conservation that has the given rank and the given sign pattern. If this is the case, then this is the dimension. There's again a formula, and R is the rank, n is the number of particles, I is the number of guys that got eliminated, loops, and m is the number of blocks in the sign matroid. So this is exactly the same thing in the presence of momentum conservation. Let's do an example. Okay. Let's look at this for 4 particles. So for example, if n is equal to 4, okay, and now you can tune in again, okay? So if n is equal to 4, this number is 2. Okay, so n times n minus 3 over 2 is 2. So we're in the plane. We're in the plane. Mandelstam was in the plane. Okay, let's make a picture in the plane, right? So let's talk about 4 particles. So now we're in the plane. So in this 2-dimensional space, and I wrote down a parametrization. I made manifest that we're in this plane, right? So zeros on the diagonal and row sums and column sums are 0. And I have 2 free parameters, x and y. And I'm now going to draw a picture in the xy plane. All right. Now remember, to be a Mandelstam matrix, that means the minors, I have to look at the minors. Well, of course, you know, the 1 by 1 minors, they're manifestly 0. They're non-positive. Then the 2 by 2 minors are non-negative. Right? The 2 by 2 minors are like x squared, so they are manifestly non-negative. And the 3 by 3 minors factors into linear factors. So this determinant is this thing, right? And this is supposed to be non-negative. All right, so let's solve this, right? So I'm dividing the plane into these cones, and the shaded regions are the allowed region. So in red, I have the name of a uniform signed matroid. So this region here, this region is y is positive and x is, I guess y is positive, x is negative, and x plus y is positive. Okay, that's this cone over here. And if you're in the interior of this cone, then the name of this cone is assigned matroid. And the matroid is a uniform matroid, but 1 and 4 are good guys, and 2 and 3 are bad guys. And here there are, equivalent. There are 3 of these, right? Because a 4-element set, I can form pair partitions in 3 different ways. Just like Mandelstam had 3 reactions. Okay. Now then there's strata on the boundary, right? On the boundary we have this matroid. Remember we had the matroid. There was this condition that now these 2 guys are in a part, and this now have a partition into pairs. Again, there's the signing, right? And I'm disregarding the origin. So there are 9 MMC strata. Mandelstam with mass conservation strata, 3 two-dimensional strata, and then 6 one-dimensional strata. These one-dimensional blue cones. There are 4 particles, and they're called 1, 2, 3, and 4. Okay? Then this blue and red set is the name of a signed matroid. Okay? So for example, down here, this says that 1 and 3, nobody gets sent out. There are 4 people in the room, and 1 and 3 are together, and 2 and 4 are together. Remember, it's a signed matroid. Right? So therefore, 1 is positive and 3 is negative. 1 is in the future and 3 is in the past. And then likewise, 2 is in the future and 4 is in the past. So this is the name of a one-dimensional stratum, which is this blue one-dimensional cone in the plane. I introduced all this combinatorics so I can name these pieces. Answer your question? Okay, yeah, very good. Okay, so there are 4 of them. Let's now introduce masses. Mandelstam was interested in this, in the situation of masses. So let's go slowly. Let's say there are 2 different masses, m and mu. They're both positive, and m is bigger than mu. Okay? So if I replace the upper 0 here in my name by this m, so then there's a corresponding partition and region, but now I have these masses. So in this example, there are 4 particles. They all have a positive mass. 2 of them are the same, and the other 2 are the same. Now, this changes my matrix like this. So this is the previous. So if m and mu is 0, that's the previous matrix. But now I have this matrix. Okay. Now here's the previous picture that I explained 2 minutes ago. Now, if mu and m happen to be the same, if every particle has the same mass, then what happens here is that these cones get pulled apart. There's still 9 regions, right? There's still 3 pink two-dimensional regions and 6 blue one-dimensional regions, but now they get pulled apart. But if now m is bigger than mu, then the regions themselves have nonlinear boundaries. So then you can work this out. You look at the conditions here. So then the names are still the same. Here it's the same naming scheme, right? So this just says who is in the future, who is in the past, and in blue it's the corresponding matroid. So the names of the regions are the same, but now they're massive and nonlinear. Now this picture equals Mandelstam's picture. Okay? This is Mandelstam's picture. Okay? So he redrew this a little bit, right? So he has this shaded region, and this one is this one, and these 2 are those 2. Okay? So it's exactly what Mandelstam did in 1958 in his paper, in the presence of massive particles, 2 of which have the same mass, and 2 other which have the same mass, and this is the reference again. Back to 1958, so If you're a mathematician, please read a paper from the 19th century. If you're a physicist, please read a paper from the early 20th century. Johannes.
Thank you, Bernd.
Okay, tell me more. Tell us.
I will tell you.
Okay. Yeah. Anyway, I'm learning physics very slowly. Anyway, I found this picture and it was kind of fun. Let's try 5 particles. We have to get in the end we have to talk about the direct product of 2 triangles, right? So if you travel to 4-dimensional Switzerland and you want to buy chocolate, right? 4-dimensional Toblerone, you need to know how to take the direct product of 2 triangles, and you need to know that this has, 9 vertices, 18 edges, and so on, right? So let's get there. Okay, so for 5 particles, there are 5 degrees of freedom, right? Then our ambient space, so, okay, if n is 5, we go n times n minus 3 divided by 2, that's 5. So now it's the same thing. There are parameters A, B, C, D, E, and I wrote down the general matrix. There's zeros on the diagonal, symmetric, and row sums and column sums vanish. So now I need to draw my picture, or Mandelstam's picture, in a 5-dimensional space with coordinates A, B, C, D, E. But, it's not so bad, right? I already, thanks to those Stirling numbers, I already know how many regions there are. So I have some clue how many regions I'm looking for. Now here's one that Balázs will hopefully like. So to be in the Mandelstam region, we have to look at the signs of the principal minors. Right? So the 1 by 1, 2 by 2 minors are trivial, 3 by 3 we discussed on the previous slide. So 4 by 4 is interesting. 5 by 5 is 0 because the row sums are 0. Right? So this is a 5 by 5 matrix of rank 4. The only interesting principal minors are the 4 by 4 principal minors. Okay, so you take the first 4 by 4 principal minor, and you get this quadratic polynomial. And to be in the interior of the region, so this should be negative. Right? This is supposed to have a certain sign. So this is a certain polynomial, homogeneous of degree 4, and it's in 5 variables, A, B, C, D, E. So this is a very, very, very beautiful surface. This is a hypersurface, the threefold. It's a so-called Igusa threefold. It's the most singular, most symmetric threefold in P4. It's dual, to the Segre cubic, and it has a million beautiful properties that number theorists and algebraic geometers love. So very, very beautiful. And we're on one side, right? This bounds our region. So let's focus here on these top-dimensional cones. So we're looking at the top-dimensional strata. So they're 5-dimensional. And since now we're back to massless, we're not doing quite the Mandelstam thing, we're back to massless. So there are 10 top-dimensional regions, so they are 5-dimensional polyhedral cones. Now a 5-dimensional polyhedral cone is the cone over a 4-dimensional convex polytope. The 4-dimensional convex polytope of interest is the cyclic 4 polytope with 6 vertices. Now, if you don't know what a cyclic polytope is, a cyclic polytope is an amplituhedron that happens to be a polytope. The definition of cyclic polytope. Okay? So this is an amplituhedron. But inside these 10 cones, so I have these 10 cyclic polytopes, they are dual to the product of 2 direct triangles, right? The product, the 4-dimensional Toblerone, had 9 vertices and 6 facets. Its dual, which is this happy polytopal amplituhedron, has 6 vertices and 9 facets, and we have 10 of them, and they fit together. Right? So let me say this again. So the analog now to this picture is not 3 cones in dimension 2, and each of these is a cone over a 1-dimensional convex polytope. 1-dimensional convex polytopes are combinatorial, not so interesting. But now, for 5 particles, we have 10 of these cones, and each of them is the cone over a cyclic polytope. Anyway, and then the dual picture sort of tells you this is all the strata. There's a little table, you know. So this is the liking, disliking pattern, right? I have these 5 particles. Because we have momentum conservation, nobody can be lonely. It can't be that one guy is in the past and 4 guys are in the future. That would contradict momentum conservation. So therefore, there are these 10 possible ways how they could be in the 2 pieces of light cone. Each of them gives an allowed sign pattern. And anyway, there's a whole story, and it's explained in the paper, and time is up. Let me get to the last slide. Okay, so in the recommender system, it will say viewers or readers also enjoyed. So shameless advertisement. Well, I was very proud, so I wrote a paper that was published in the Journal of High Energy Physics about a year ago. It was amazing. First of all, Bruno is a super nice guy, so he wrote a paper called Splitting CEGM Amplitude. So I already mentioned the other day, so CEGM is something I like. Whether or not it's physically relevant, maybe not. But this was amazing, right? So we wrote the paper like in December, right? And then we submitted it, January 10. We had a referee report, February 8, and was published at the beginning of March. You ever heard such a thing in math? I mean, it's unbelievable, Anyway, this was very fun. I wrote a paper with Mate Telek, now based in Budapest, on co-positive geometry. Now here we're looking at the co-positive geometry in the Lee-Pomeranski formulation. It would be very, very interesting to explore the co-positive geometry in other representations. There's minimal kinematics, so I published a paper in the journal called Moduli. It's a new journal. It's a math journal, so it took over a year with reminders to the editors and so on, and maybe eventually it got published. And finally, we have one with a team of 4 fantastic young people, Barbara, Victoria, Bella, and Bailey, on graphical scattering equations. So even if you didn't like this talk, maybe you like one of the other ones. Thanks.